So, good morning to everyone. I would like to thank you, the organizers, for giving me the opportunity to present my research work in the first international online conference on nanoscience and nanotechnology, 2nd December 2017. So, today I'm going to present my work in the title of Anti-Reflective Effect on Human Lungs and Lines A54 of the cadmium selenide nanoparticles extracted from psychotoxic effects in the investigation of bioelectronic application. So, Nano 2017, the conference teams under the outline Material for Health. So, today I am going to present the order of presentation, motivation, preparation, and characterization of cadmium selenide nanocrystals, results and discussions, and conclusion. In the introduction, in order to understand the interrelation between the structure and the physical properties of nanocrystalline materials need to be synthesized on both atomic and nanometer scale. In the microstructure, features are more important. In order to the grain size distribution on morphology with the composition profiles across grains and interfaces with the nature of defects. In the objectives of the recent studies, would like to tend to provide a controlled and scalable process for biosynthesis of monodisperse and highly stable nanoparticles. However, a wide number of bacterial species have been used in green technology to research alternative method for the synthesis of nanoparticles. So, I'm going to present the motivation of my research work. So in the first point, the comparisons of the psychotoxicity effects between cell-particle interaction, viability test, membrane integration, and oxidative stress were investigated. In the longitudinal optical phonon shift slightly due to strains, whereas strong low-energy shoulder shifted can be explained within a model for surface optical phonons. In third point, photocatalytic activity of the cadmium selenide nanoparticles were investigated by exploiting photocatalytic degradation of RHB, which exhibit antibacterial activity over a wide range of bacterial species and in particularly against of P. vulgaris where it outcompetes for other commonly used S. aureus, E. coli, P. vulgaris, and E. herminil, well as tested in the present work. So, in the resultant discussion, in figure 1 A2D, the XRD pattern of CDA-SC nanoparticles. In figure 1, represent the XRD pattern of CDA-SC nanoparticles treated at 900 degrees Celsius for 15 hours. A sharp peak at 2 theta is 25 degree appears in the XRD spectrum, which corresponds to 1 plane reflections of cadmium selenide nanocrystalline lattice. A strong XRD peak associated with the triple 1 plane suggests that the CDSC nanoparticles grow in a professional orientation. Another peak was also observed at 2 theta, so that is 45 degree with a broad and low intensity which represents 103 plane of the hexagon structure of CDSC. XRD peaks showed triple 1 peak along with other related to 200, 103, 311 and 203 planes or hexagonal structure. When the temperature is increased up to 900 degrees Celsius, the crystallines become highly oriented along triple 1 plane and the other peaks are found to be gently suppressed. A variation of the microstructural properties of CDSC nanoparticle with a standard annealing temperature are summarized in table 1. The grain size of the CDSC nanoparticles can be effectively tuned between 22 nanometer to 44 nanometer respectively. Moreover, To increase the surface energy volume due to the presence of nanograins also contributed towards the varying magnitude of strains in the nanosamples. In the present study, CDSE nanoparticles show a reduction in C-axis, which indicates that the nanocrystals are experiencing compressing force in the A direction. The hydrothermally grown CDSE nanoparticles shows larger A value compared to the standard value, which means to indicate tensile strength along the C-axis. Furthermore, it is standard due to the presence of lattice with reduced grain size almost along the nanograin particles are found to have different crystalline structures when compared to the polycrystalline or single crystalline counterparts in thin film or powder samples. This is mainly attributed due to the interference the number of atoms in the nanoparticles reduce the extra free energy are associated with surface morphology. In figure 2 shows that the photoluminescence spectrum of cadmium selenide nanoparticles, the excitation wavelength is 650 nanometer and the PL peak is about 703 nanometer. The luminescence curve from the surface states around 698 nanometer to 703 nanometer also been observed. Thus, the peak of the eigenstate is strong and the narrow and the emission of surface is seen with a major rump indicating the quantum confinement effect. Thus, the photoluminescence spectrum is dominated by a narrow and strong band edge emission tunable in the red region of the visible spectrum. So, indicating a narrow size distribution of the cadmium selenide nanoparticles is possibly comparing to the recombination of luminescence of shallow drop and surface defects, localized excitation, and intrinsic excitance. The large band at 703 nanometer can be attributed the radioactive recombination from deeper defects and impurity levels. So in figure 2 displays the photoluminescence spectra of a cadmium selenide nanoparticles such as the one of usually treated by the impurity and vacancy complexes lies in 1.76 electron volt is observed with corresponding to the energy band gap of the cadmium selenide nanoparticles. In this paper, we can represent the cadmium selenide nanoparticle centered at 1.76 electron volt. In our knowledge, cadmium selenide nanoparticles we justified by the fact that these charges for convenient and partially ionic crystal semiconductor compounds are not too significant to size of 2 to 5 nanometer in the circumstances to suggest that the interatomic distance and the bond angle slightly decreases, the situation begin to significantly changes used in the term of the longitudinal and the transverse optical phonon to distinguish between the nanoparticles. Finally, cadmium selenide nanoparticles under our investigation are a broad and very strong quantum yield or several tens of percent band invisible region of the spectrum. In figure 3, to compare the bare electrode, the modified electrode of cadmium nickel cadmium selenide revealed several redox complexes at the electrode interfaces in figure 3 and 4. In figure 4, the cadmium selenide nanoparticles showed two redox complexes at oxidation peaks potential of 1.33 volt and reduction peak potential is 1.28 volt respectively as shown in figure 4 C and D region. The observed redox complexes are attributed to the cadmium selenide quantum dots as represented by other researchers. Meanwhile, the oxidation peak current and the reduction peak current of selenium 2 minus and cadmium 2 place were observed at minus 0.89 volt to minus 1.84 volt respectively as illustrated in figure 4E and F. Small oxidation peak current is 0.56 volt as also observed in figure 4D which has been attributed to CD which tilts the 0.2 volt. In figure 5 suggests an effective use of the modified electrode to the electrolyte owing to better ionic diffusion due to the quantum confinement of the material. In figure 5, such parameters as a diffusion coefficient D and the surface coverage, which peaks for the convenience only the results from the reduction peak currents are reported. In the calculated diffusion coefficient was found to be 2.9 into 10 power 6 centimeters square with the correlation coefficient is 0.98 and the surface coverage was found to be 1.38 into 10 power minus 3 mole centimeter square, which was calculated values reveal the formations of the monolayer at the electrode interface and a diffusionally controlled system, which indicates is highly catalytic, can be applied to various electrochemical systems to confirm the electrochemical kinetics at the electrode interface impedance measured covered as shown in figure 6. The Nyquist plots were recorded at frequency ranging 100 Hz to 25 MHz and revealed the electrical properties of nickel-doped cadmium selenide apparent by semicircular and linear behavior of the system. In figure 6A was also used to stimulate the specific parameters. The semicircular portion observed at higher frequency corresponding to the electron transfer limited process, whereas the linear part is characterized to the lower frequency range present diffusion limited electrochemical process, thus confirming a very fast electrotransfer process. In this view, the observed results are in accord with the Nyquist theorem. In figure 7, UV spectrum of cadmium selenide nanoparticles, there is a broad peak in the UV curve which is centered around 350 nanometer. As the cadmium selenide nanorods grow larger, the longer axes grow beyond the confinement regime and the excitation peak only depends upon the shorter axis on the rods. In this region, for the redshifting of the excitation peak, the spectral studies are carried out to detect the lower concentration of the defects rather than the optical observations, which is the mechanism where the impurity of observed of light, the rise to be bound exit state from it return to the ground state at binding in accordance with the color creation mechanism. The absorption spectrum of the cadmium selenide nanoparticles, it shows two distinct absorption peaks. The appearance of the kind of minor peak at 285 nanometer corresponding to the N2 pi transition and the major peaks with maximum absorption are around 457 nanometer represents 2 pi transition and the absorption peak. The value which is maximum 457 nanometer with the addition of glycine nanoparticles result in the formation of peak centered at 457 nanometer. To estimate the bandgap of the semiconducting nanoparticles, include the analysis of the photoluminescent emission is strong. As a quantitative estimation of the bandgap is difficult as the photoluminescent energy depends strongly on the nanocrystal surface. Furthermore, the determination of the absolute band position is not possible to all. In figure 8 and B shows typically the UV absorption spectra of the rhodomain B at different time intervals. It can be seen clearly that the relative intensity of the absorption peak at 315 nanometer of RHB increases rapidly as the exposure time intervals. The rhodomain B was strong completely degraded after 60 minutes, which is faster than the degradation value ratio of rhodomain B in the black and the dark region, as shown in figure 8b. Compare the hexagonal cadmium selenide nanoparticles of H2O2 is about 89% and the 37% of the rhodomain B we degraded after 30 minutes. When only the hexagonal CDSC nanoparticles and only hydrogen peroxide were used specifically by the above results, review the presence of the hexagonal CDSC nanoparticles can effectively escalate the photocatalytic degradation. The role of cadmium selenide in the photocatalytic degradation of RHB. Furthermore, to investigate by repeating the rhodomain degradation with the same hexagonal CDSC nanoparticles and adding 30 minutes in each parameter as shown in figure A. However, Photocatalytic performance was found to increase gradually up to 91% after 4 cycles, which exhibit a stable photocatalytic activity and emphasize the chemical stability of the synthesized hexagonal CDSC nanoparticles as shown in figure 8a, b and c, that the CD cadmium selenide act as a photocatalyst. When the time increases, the degradation percentage also increase. The efficiency of the cadmium nanoparticles was found to be 91% effective. In figure 9, A2D anti-battle growth of cadmium selenide, which was the disk diffusion method, has been used to evaluate the antimicrobial activity of nanorod capped with different capping agents against gram-positive and gram-negative bacteria. In these nanoparticles capped with the SRS showed minimum zone of the incubation, indicating less additional activity of E. coli. Capped cadmium selenide nanoparticles showed maximum zone of incubations. For additional the antibacterial behavior, the surface modification is an important factor. In the present work, we represent the explanation of the antibacterial behavior based on the chemical structures of the stabilizers used in figure 9a2d. It is known that the cadmium selenide nanoparticle exhibits antibacterial activity over a broad range of spectral and the particular against positive gram. Its outcome 4 is commonly used as SRS, E. coli, P. vulgaris, and L. As well, testing of the 4 different cadmium selenide nanoparticle concentration of 0 millimole, 2 millimole, 2 millimole, and 10 millimole solutions. Each of them has a lone pair electron and can be seen bear electric charges depending upon the solution pH. It is well known that the cadmium and selenide can act as a pair of binding sites for the metal signs. Thus, the results showed a significant loss in the viable cell number of all 4 species, in 5 mol and 10 millimole being the most effective and 2 being the worst. It is provided only a slight improvement from the control. The effect of the particle size is also tested during the cadmium selenides. In the experiments have used to show minimum antibacterial growth. In the experiments, they have used different bacterial species, which indicates the size used where 1 micrometer to 30 to 50 nanometer were tested on the E. coli. A result showed that the smaller particle size could reduce bacterial growth in some cases up to 99%, while the larger particle size of the same condition only managed 30 to 50% incubation of bacterial growth, as shown in figure 10. For MTT assay, the medium from the well was removed carefully after incubation. Each well is washed with MEM for 2 to 3 times and 200 microliter of MMT was added. The plates were incubated of 6 to 7 hours, incubated for cytotoxicity test. In figure 11, the suspensions of DMSO was added in all the wells. After incubation, the 1 mole of DMSO was added to each well as mixed with the micropipette and left 45 seconds. The presence of the viable cell was visualized by the development of the purple color due to the formation of Forsman crystals as shown in figure 11. The suspension was transferred to the curvet of a spectrophotometer and the optical density value was read at its 570 nanometer by using DMSO as a blank. Measurement was performed of the concentration requirement of 50% incubation was determined graphically. Therefore, the percentage cell visibility was calculated using this formula, so which means the percentage cell visibility equal to A57 of treated cell divided by A570 of the control cell into 100. So the cell control and the sample control is induced in each assay of compare the full cell viability measurements. In the investigation, different concentrations of the cadmium selenide nanoparticle was treated with known quantity of cell and the percentage cyclotron each dose value was measured by using MPT assay as shown in 13 also. After exposure of the cadmium cyanide a long and the dosage depends significance decreases in cell viability either by MPT test was observed. The dose response curve of the cadmium cyanide induced in viability was estimated as an IC50 of 50 microliter per liter. After the same testing condition, no mortality was evident after the cadmium cyanide exposure. The effective cytotoxicity active of the as synthesized cadmium nanoparticle against A549 may be attributed by the small particles, so that is 5 nanometer, a large surface area which enhances the absorption of biomolecules and chemicals on cadmium selenide and supports cellular influences. Although it is reasonable to assume the correlation between the chemical compositions of the cadmium selenide nanoparticles become more important for the mechanism of the functionalization of either biology or the pulmonary material application for or respiratory diseases. This is yet a lack of information about toxicity of these material or biological systems. In this work, exposure of A549 cell of the cadmium selenide resulted in a significant time and dosage dependent cytotoxicity of the cadmium selenide showed negligibly cytotoxicity. From the figure 15, HRTM images of the cadmium selenide are synthesized in the work and it is good shape with a less pronounced stacking fault, with the measurement value of the mean diameter and the length is 25 nanometer and 50 nanometer respectively. This could be attributed to the reason in the low resolution HRTM images generally it is not possible to the different particles is clustered, aggregated or clustered form useless special purpose of techniques, which means though the majority of the cadmium nanoparticles exhibit rod-like morphology, few particles with spherical shape are also seen in agglomerated condition in figure 15F. In figure 15F shows the lattice fringes of cadmium nanoparticle corresponding to 002 and 100 lattice plane up to the Wood's hexagon structures. The formation of the individual nanorods of cadmium selenide with a narrow size distribution is evident from the HRTM images. As in figure 15E shows the lattice fringes of a single nanorod and clearly visible lattice plane endorses the formation of the well crystallized single crystal of cadmium selenide nanorod. In the XPS studies, XPS is a very sensitive tool to find over the elemental and the chemical composition of synthesized nanorods. In our XPS spectrum, the depth analysis signals were found from 1 nanometer to 25 nanometer from the figure A16A to C. Due to the many channeltrons of the detection limit has been increased. So which means the instrumental resolutions under the condition of 1 electron volt full width of maximums to the cadmium auger 974.39 electron volt. The C auger, the value is 1069 electron volt level. In general scan of our CD XPS spectra, C1S, C3D, O1S, C3P, O auger, CD auger, and C auger. The cadmium 3D peak in each cases has a doublet due to the spin orbit splitting result in 3D 5 by 2. So that is 4012414 electron volt. The CD 3 by 2 is 411 electron volt of cadmium selenide agrees well with those values. So which means the CD 3D core level could be satisfactory for the spin orbit pair. In our knowledge, the relative intensity of the cross-sectional surface composition of other elements which has lower binding energy peak at 3D, CD4D that is 54 to 32 electron volt and cadmium 3D is 63.26 electron is active for the metal sulfide while the other peak has selenide 3P that is 199.85 electron volt has been assigned to more oxidized peak in the state of the sulfur is P2P that is 179 and P2S is 324.2 which the separation of 1.2 electron volt. The ratio of the intensity of the two components was 2:1 ratio. In in figure 17A and B represents the Raman spectra of the cadmium cylinder rods with 10 micrometer diameter and 228 nanometer micrometer respectively. The cadmium cylinder bond of the first and the second order peak can be clearly indicated the 41751 centimeter inverse and 623.29 centimeter inverse. From the figure 17A, it is clearly indicated as a transverse optical and the longitudinal optical of two yellow phonons respectively in the yearly study of the Raman signals in bulk CDSC in the phonon LO plus TA at 219 centimeter inverse, which excitation wavelength were 671 nanometer and 488 nanometer respectively. The deconvoluted band of cadmium selenide in figure 17b was observed 190 centimeter inverse, 225 centimeter inverse, 259, 280, 298, 335, 350, 417, and 623 nanometer. It is also pointed out these bands are much more enhanced with the laser excitation of 632 nanometer and the UV is 325 nanometer respectively. The most prominent mode of the 280.97 centimeter inverse can be attributed to the first order cadmium selenide additional optical phonon and another mode of 417 centimeter inverse to the overtone of 2LO mode in the smallest gap between the nanocrystals. So which 632 nanometer excitation wavelength and the light polarized parallel to the long dimer axis reveal the most intense phonon mode. In this mode, which appears is 190 nanometer, 190 centimeter inverse is superimposed with a broad background between 175 centimeter to 350 centimeter inverse and a weaker feature of due to the 2LO scattering. That means 417 centimeter inverse. The first peak can be attributed to scattering by surface optical modes, which was previously well investigated in the CDSC nanorod. So, in the acknowledgements, I gratefully acknowledge the research funding from the UNESCO University of Africa Chair in Nanoscience and Nanotechnology Laboratories, College of Graduate Studies, University of South Africa. So, I wish to achieve the grand success, the first international online conference on nanoscience and nanotechnology. Thank you.